Okay, so I have the entire lab set up for you guys, so it'll be fast when we get back there. All right, so in terms of just general stuff, your test has some lab-based descriptions and data analysis and procedure analysis to it. So if you're not one that has done, like, oh, let's say, I know Christian's done this twice or 3 times now, heating of the crucible, right? And understanding how when to stop the heating process. Those people are going to be phenomenal on questions regarding crucible heating because they've done it. But it doesn't mean that the rest of us are not responsible for that information. In terms of doing colorimetric or spec 20 work, we all should be very familiar with how to do that. Some people are more hands-on with that, some people are more just observing, but you're still responsible for knowing the concepts and the procedures and like data analysis, error analysis. So make sure that you're like even the titration lab from yesterday. Some of you guys, you definitely got to back conquer, and that's totally fine. But you do need to go back and read people's stuff because some people are making comments like, "Is this right in terms of math?" Everybody should be doing the math and like cross-referencing their process so that you're understanding the process. Okay, so in terms of what we need to do for the stoichiometry of hydrogen peroxide percentage, let's go through the whole shebang, no stops. Okay, what do I have to start with? Maybe somebody can give me some data. Milliliters of what, Kui? Can you tell me the milliliters of your potassium permanganate used? Okay, so 70 point what? 24. Some of us are going to have obviously different numbers because we did not use the huge saline 30-ish% one that's supposedly there. So we use 70.24 milliliters of 0.020, I'm going to do millimoles because that's what most of you guys are probably working with right now, of potassium permanganate. I would just be writing this process down just in case because, I mean, you should be able to do this on paper easily. Okay, so you take your volume times your molarity, and you basically get moles or millimoles of potassium permanganate. Keep going. Next up, let's go. Say again? Okay, let's just get to the permanganate ion first, and then we'll use mole ratio. So 1 millimole of potassium permanganate has 1 millimole of permanganate MnO4 1- ion in it. And then according to your balanced chemical equation, which you guys should have on your Google Doc, what was the ratio between permanganate and hydrogen peroxide? 2 to 5, was it 2 permanganates? Okay, so 2 millimoles of permanganate ion for every 5 millimoles of hydrogen peroxide. Okay, this is a note to self. When we start talking about the quantities reacted are actually the true permanganate ion and the hydrogen peroxide inside of the solutions we had. Was the entire purple solution potassium permanganate? What else was in it? Water, right? So there's water in there, and so not all of that volume is actually potassium permanganate. There's a lot of water in there as well. And not all of the volume of the hydrogen peroxide used is hydrogen peroxide. What else is in that solution? Water. So we have to differentiate the mass of the solution versus the mass of the actual hydrogen peroxide in the solution that reacted. So that's kind of what we're doing here with this mole ratio. So as we go through the determining of the true moles of potassium permanganate when we multiply by the molarity, and then we go to use the mole ratio, we're finding the true moles or millimoles of hydrogen peroxide that react. This is how many moles of hydrogen peroxide that reacted with that amount of potassium permanganate at the equivalence point, which we found to be at the point when what happened? Change to pinkish, right? Okay. So then from here, we got to go to, I'm going to go to moles now just so I can work in moles and grams. So 1,000 millimoles of hydrogen peroxide is equal to 1 mole of hydrogen peroxide. And what's the molar mass of that guy? 34.02. Oh, something. Okay. Grams of hydrogen peroxide is equal to 1 mole of hydrogen peroxide. Okay. And then this gets you to grams of hydrogen peroxide actually reacted, which was like in this hydrogen peroxide solution. So we'll get this value. Can somebody get to that for me very soon? Since this is y'all's data, could you maybe calculate for me? 0.11 what? 9 grams of hydrogen peroxide. All right, so supposedly that's how much was in the solution that you guys reacted. Now, that's just the total, that's the top part of your mass percent. So So in terms of finding the bottom, the total mass of the hydrogen peroxide, you guys had one thing you absolutely had to use. What was it? Density, right? So you didn't mass your initial solution of hydrogen peroxide. Wait, what was y'all's initial for this trial of the hydrogen peroxide? Yeah, be louder for me.
1.02.
So initial volume 1.02 milliliters. I need your I need your hydrogen peroxide initial volume. You used 1 milliliter, so 1.02 or just 1? Just 1 milliliter. Is that what you said? Okay. So we have 1 milliliter of hydrogen peroxide solution, and then I put the densities for all of you guys based on the solution that you guys used. I had to try to make sure I just masked them and then found the volume and then recorded density. Kui did that as well. So Kui, what was y'all's density for the solution you guys utilized? 1.025. 1.025 grams per 1 milliliter. And this is still hydrogen peroxide solution, not just true hydrogen peroxide. So then 1.1 times that is 1.025 grams of hydrogen peroxide solution. So using the grams reacted with potassium permanganate divided by the grams of total solution times 100, what do you get? What'd you get? 11 point what? Okay, 11.6%. Okay, so this is the hair salon. Was that the one with the, I said 3M?
Yes.
Okay, so the 3M one, hair salon, 3M solution. So it's not 3 molar, let's be honest, but it's 11.6%, supposedly. Now, do you guys understand your process? All right, I'm moving on. I'm videoing too, but you guys, I do not want to do your data analysis for you. I don't. I want you guys to be creative, think through what you're talking about, and then problem solve together. Yes, ma'am.
If we dilute our sample, does that make
No, because you still have the initial sample that's got the hydrogen peroxide that was in it previously. Okay. All right, go to my website for me. I'm going to show you guys a couple things. Pull out the lab to read, and then let's talk briefly about what we read about, because I'm expecting that you are prepared to do this lab today without much guidance, but I'm going to be back there with you guys as you go. So go to my website under homework, and I'll show you where the, well, I'll just ask for you guys to find it yourself. But it says Friday homework. There's a link for today's lab. This is like INLO, or Beers Law INLO briefing. Beers Law INLO briefing. Give me a thumbs up when you're there. All right, you pulled out the lab that you were to read. All right, I need more participation vocally, okay? So from your reading, what was important from the background, introduction material? Hands up, let's go. Cassie. So the parts of the metal, so parts of the alloy. Okay, so the alloy information, and how in that alloy you have a mixture of metals, and that mixture of metals is going to give you, when reacting with acid, which we're going to be putting this in nitric acid, we'll pull one of the metals out. So alloys info with metal mixtures. And so I know I have your lab notebooks, and I know this is not a Google procedure one, so I would be annotating some of these details, because this would be like purpose, background, a little bit of safety, a little pre-lab, right? So this is stuff that you should be having. And what I would do is put in something that I could just cut and paste into my lab notebook. So try to, the lab notebooks are a little narrower, so keep it in the middle of your paper, you can cut and paste. Christian, tell me something else.
The visible and ultraviolet light.
Okay, so the visible light, and that's what we actually are using, visible UV. With the Spec 20s, we're shining light at these things, and they're causing certain colors to appear because of electronic excitations, which is based on the electron configuration. So visible and UV light cause, I'm going to say colored compounds to be visible. And in our lab, what's our color compound? Say again? What's the color compound that we're utilizing? Copper, right? Copper 2. What color is that? Copper 2 is blue. Thank you. Why are you guys being so quiet? Give me some information here, okay? Give me one more thing, Megan.
From the background, I was going to give you like
That's what I want to know. Can you give me some more?
But it's in like, it's used for Beer's law, like it's one of the variables that gets used.
Okay, so I'm going to scroll down just so I need more space. So in terms of Beer's law, here's what I need you to know. A is equal to A, B, C. You should know what these variables represent. You should know the units generally that we use, and you should know the correlations, meaning direct relationships or indirect relationships that we would see. What is big A, everybody? Absorbance, and that's what we'll measure in the lab. Okay, so that's what our spec 20s and our colorimeters, which I have some colorimeters which might be a little interesting to use for today. That's what I will be measuring in the lab. In terms of what we're also kind of measuring in the lab, but based on our own preparation of those solutions, what are we going to be preparing? Say again? Say again? Okay, so we have the brass. We're going to dissolve the brass. We're going to make a solution, and we're going to prepare it to a certain concentration. Okay, so we're going to then have control over concentration, which we're going to use molarity today. The last time we did this, we used micromolar or micromolarity because we had very, very, very small quantities. But we're going to use molarity today. All right, so what's B? Okay, so it's called the path length, and it's actually the cuvette, which you have here. The light goes through it, right? And your solution here in the middle has got some sort of colored compound in it that's absorbing the light. And so the light that goes through, or the light that goes in might be really harsh light, you know, a high amount of intensity, but the light comes out might be smaller because it is being absorbed by the sample. So the path length is actually like the cuvette width. So in order to control that variable, what do we need to do in our lab? Use the same cuvette supposedly every time. We should be trying to do that. And then what's A? It's a constant, but what's it called? Proportionality constant. I'm going to call it molar absorptivity constant. And so it's actually a constant for every solution we have will have a different constant because it's with a different ion or different selection of ions. So the A is not something we'll ever actually write out for now. Maybe maybe in a month we get kinetics. But it's just a constant that we will just assume is constant. We don't really need to know what it is. Cuvette width is generally regarded as 1 centimeter. It's maybe bigger or smaller, but we kind of just say, okay, it's 1 centimeter, and that's what we call it a constant as well. And we can only call it a constant if we use the same cuvette. So what are the two variables we can manipulate? The concentration and so the concentration, which is the sample we are using, right? And no, we're not going to modify the cuvette. The cuvette is going to be one thing. Right, so the concentration we manipulate, it will cause the absorption to change. Concentration goes up, what happens to absorption? If concentration goes up, can we get a consensus here, loud and proud? Okay, so as you concentrate your sample, the light can't get through, so transmission goes down, but absorption goes up. Okay, so would you say that's a direct or indirect relationship? Direct relationship. So you'd say these are proportional. Yes? Okay, just some terminology to throw at you. All right, so that's our Beer's Law talk, and then we'll be utilizing that throughout the procedure. In terms of the safety information, what should you be regarding or including? The strong acid. We have a strong acid. What do you need nearby, just in case you spill it, CJ? Baking soda. Sodium bicarbonate. Did you balance the NIE? Take a second and balance it. Do you guys see that on page? It says page 2 of 4. You see that one? Okay. Did you balance it? All right. Everybody else take a second. Marcus, tell me what you did to balance.
On the copper.
Tell me the half reactions first. Yeah.
Copper solid goes to copper 2 plus aqueous.
Okay.
And the minus added 2 electrons per example.
Thank you.
Then your next half reaction is NO3 minus aqueous.
All right. Before we move on, this nitrate is from nitric acid, right? Why am I not writing nitric acid? So the H makes an ion Y. because it's a strong acid, right? If it were a weak acid, I would not be separating those. It's a strong acid. So that produces what?
NO2 salt.
Gas.
So gas.
So nitrogen dioxide is a brown hazardous gas. Okay, so keep going, Marcus.
On this one, I added a H2O to the right, and on the left, I added 2 H pluses, and then 1 electron.
To do charge balance. Good. Okay, everybody, charge balances? Are they balanced?
You have to multiply 2 on the bottom.
Good. So you're gonna multiply the second reaction, half reaction by 2 to give you electron balance is what I meant by that. That electron balance will cancel out. What's your total reaction?
4H plus 2 NO3 minus plus copper 2 copper 2 2 NO2 and then 2 H plus.
All right, so there's our balanced chemical equation, NIE, and everybody look at the data provided for you below that in the paragraph. It says, I'm giving you a piece of brass, so I'm giving that to you. I'm approximating it's 1.5 grams, but we don't know that exactly right now, so let's just set up this calculation. Okay, so assuming that the entire brass sample was copper, is that a true statement? No, right, but we're assuming that, because if we can assume that the entire 1.5 grams of copper, brass is actually copper, and we add this nitric acid on top of it, who's the limiting reagent? The copper in the brass, right? Who should be excess? Nitric acid, which means that all of the copper should come out of our brass sample, assuming that we have a good sample of it. So 1.5 grams of brass, aka the copper that we're assuming. I want you guys to figure out how many milliliters or liters of the nitric acid solution we need. Stoichiometry, go. Now, that 1.5 grams we're just using the placeholder for now. We'll go back and recalculate in future mass. I mentioned that before you proceed calculations. I just wanted to show, oh, I didn't have to. I added this step in because I was trying to show this to this. I could have just left it as copper. This copper is a 1-to-2 ratio with that as well. You don't have to have the step. I didn't have it on my paper and I just added it. You don't have to have it. It's a 1-to-1. Any mental guesses? Okay, here's how I would approach it. It's for easy math. What would you multiply 1.5 by to make it easier? Okay. I was going to say 1,000. Can we say 1.5 times 1,000 down here? So what's 1.5 times 1,000? So you move the decimal how many over? 3 spaces over, so 1, 2, 3. 1500, is that what you said? Okay, so 1500, check, check. I can do 1500 divided by 15 versus 16. What's 1500 divided by 15? 100, okay. So you did 15 times 10, it would only be 150. So it's going to be 100. Okay, so now I can work with 100. Okay, so check, I've used this one, I've used this one, I've used this one, and I know that's low, so it actually would be more or less than 100. No, yeah, it would be less than 100 because you're divided by 16. Okay, so I can do 100 times 2, 200, okay? And then I can do 200 divided by 60. Well, 60, 120, 180, so almost 3 because we went low here, so it's going to be about 3. Calculate. 2 point what? 98. See, we got this. We just have to practice. Not grams, milliliters, right? Milliliters of nitric acid. And this is stock solution nitric acid, so I will be helping you with that, okay? Just note that you will have to modify this based on what? Your sample of brass, okay? Because everyone has just a slightly different one. I just took some brass and had my dad cut it, so we'll see how that worked out. All right, so we're going to go here. Oh, no, sorry. Let me make sure I covered all my bases. Okay, in terms of what I need from you by the end of this, you guys see the conclusion, post-lab questions, and then down the road, it's on page, not paged actually, it's page 3 and 4. You guys see those? Okay, I need those to be done Monday, and those will be a great practice before your your test. The free response questions attached to the back, do you see it says like 2003 free response and 2003 response? It's the last page. Do you see those? Okay, I think those are fantastic ones to do to practice your Beer's Law. They might really help you on your test. Okay, so do try to include those and just put those in your lab materials. It'll be like an extra analysis question. And then I'll give you a lab notebooks back Monday and you guys can take those things in. Okay, so let's talk about what we're going to do. And I'm going to ask for you to follow along with me here. You guys got this pulled up? Yeah? Just in fear that I'm not videoing, I just need to make sure I am. Yep, good, okay. Alright, so we're going to figure out how to do our mass percent of copper and brass. Now, the idea behind it is we're using techniques, spectroscopy, using light, so we need to be very aware of how things absorb and how we track how we decide our wavelengths. So, in terms of looking at the graphs with me, look on your computers, that's fine. But I want you guys to tell me, in this sample here, we have copper 2 nitrate. Where do you see the peak absorption? 650, 670? Okay. How about this next one, where you see the peak absorption for copper, copper 2 sulfate is what this is supposed to be. 6 what? 6, between 650 and 680-ish, okay? What was the common denominator between these two graphs? What was the common thing between these two graphs? Say again, JT? Copper. All right, so who's controlling the absorption? Copper. How about nitrate? Is it doing anything? No, because copper is blue. Copper 2 is blue. Nitrate is clear, okay? What's the as you can see here, copper being the commonality, still absorption peaks at around 650, 670. So sulfate, what color was sulfate? Clear, okay? So the only things that we're going to be using for absorption are things that have color to them. Clear stuff's going to let the transmission go 100%, absorption goes 0. So looking at this graph, why is there no absorption? This is the zinc nitrate one. Because what color is zinc 2? Clear, obviously there's no absorption, right? And what color is nitrate once again? Clear, okay? So you cannot do spectroscopy with anything that's clear. Point taken? Moving on. Because you don't have any light or any species to absorb the light, you're just going to be wasting your materials and time, okay? Same thing kind of happens here, but we have a different species who's absorbing light here. Iron 3, where does it absorb light? Or the maximum light? Maybe about 390, 400. It's pretty low on the spectrum there, okay? All right, so we know now we have to take all these absorptions or all these wavelengths into account. We run our absorptions at every wavelength that we have here, which I ran these for you to see the peak absorption. The peak absorption for copper is definitely at 670. So where will we put our spec 20s or colorimeters at? 670, or as close as we can get to there, okay? All right. Oh, and actually, we can look over here at this graph. Peak at about 680 right there, actually. See 16? To 0.23, 0.24. So I'm going to go with 280. So try to hit that 280 nanometers, okay? So writing that down for yourself for later. All right, so why do we want to use a particular wavelength when determining the absorption of a particular chemical species? Why do you think we need to find the perfect wavelength? Say again? So the most of we want to get most of the copper ions accounted for. So we have to use the maximum absorption to get the most precise data we can in terms of concentrations that we'll be finding. All right, so we will always measure between 400 and 700 nanometers because that's our visible wavelengths. That's what we can see. We can't see in UV and IR, so we can't be using those to detect our own concentrations. So I gave you some background on Beer's law, so I feel like you're pretty good with that. It's called Beer-Lambert law because there were two guys that made it up, but we just call it Beer's law. Remember ABC? Okay, so remember that for yourself. You guys can read through that on your own time, okay? Now, the idea of spec 20s and the analytical tools that we will be using, we went through this in Unit 1 with the relationship being negative log of the percent of the transmission or transmittance. So I think that understanding that transmittance is important, yes, but absorption is what we're looking at in terms of the law itself. So we could technically measure in transmittance and then go do negative log of percent transmittance and then have the absorption ourselves. But we're smart now, right? Let's just make it measuring absorption. Good with that? Measuring absorption can give us a quantity for concentration. All right, so we got that. We know how to read our graph and find the strongest absorption, which is around 670, 680 nanometers. So, you guys remember what a calibration curve is supposed to be used for? Why do we need a calibration curve? Maybe turn and talk to the person next to you for a second, just because you're thinking. All right, come back to me. Anybody got to have the value of a calibration curve? Say again? I need to know, like, why do we value calibration curves in chemistry? Okay, so we can find our linear relationship, in this particular lab, what are we going to find our linear relationship between? Absorption and concentration. So if I have you test any other concentration, if I give you a new unknown concentration, and I say, find the concentration of this, what are you going to do? Find the absorption how? On the spec, and then you're going to go, now what? Okay, look at the line you have graphed or your calibration curve you've created, and if you said, oh, the absorption's blah, 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 you would say, okay, there's the absorption, track, ooh, that's where it hits the line, track, ooh, there's the concentration. So the value of a calibration curve is it can give you ultimate predictability of any unknown solution in terms of Beer's law. Ultimate predictability, taking absorption and finding concentration. So you good with that? Okay, so we have to make our own calibration curve because we don't have this curve for ourselves already because we've never done one with copper 2. Okay, so this is background information. It's more about the spec 20s and how to use them. What I actually need to tell you, I'm thinking a lot of this stuff is later on in our AP Chem lives. Okay, good. Nothing there yet. Okay. All right, so here's what we have to do. Here's your steps. You guys on the slide with me? Okay, so here's what we've done so far. We looked at the graphs. We know the species, the copper 2 species we're looking for. We know the maximum absorption or wavelength that they will absorb the most at. We understand the relationships between Beer's law variables. Now we need to create a calibration curve of known copper 2 sulfate solutions. You need to test 5 samples. So you're going to have 5 molarities, 5 absorbances. Data table. Maybe write that down for yourself. 5 concentrations, 5 absorbances. Before you start testing, what do you have to do with your colorimeter or with your spec 20? Calibrate it, right? Meaning put a blank in, let it read the blank first, okay? So what I would do is just have one person or 2 people starting dilutions. I have a couple out there already for you, so I've got 1 molar I've got 0.5 molar, and I have 0.4 molar. So I've got 3 of them. If you wish to use those, you need to get 2 more dilutions in. Okay? Now they are dispersed around the lab, but 1 molar, 0.5 molar, and 4 molar. Just I've got those prepared for you. So make sure you're showing your concentration. Show me your dilution equation, how you're going to find these find the concentrations. Pre-calculate how much nitric acid you need. You already have the template for that, right? Based on the mass of your brass. Good. React the brass with the nitric acid. I will do that in the fume hood for you. You just need to bring me a beaker with the brass in it, and I'll add your nitric acid on it based on your proof of your math that you're going to show me. After, and this is very important, I will have strong acid in your sample. You need to bring it carefully back to your desk, and then you're going to take that liquid from your beaker and pour it into a 100 milliliter volumetric flask. You with me here? Okay. But you're going to add water, and I know it says dilute with water first. You can dilute with water first because Truly should add acid to water. So put a little water in your flask first, then put your acid on top because there won't be that much, and then add more water to dilute to a 100 ml sample. So the 100 milliliter volumetric flask to the etch line, and that will make it safe enough for us to utilize in the Spec 20s. After you get your sample here, this will be your unknown brass copper 2 sulfate solution or copper 2 solution. What are you going to do with this? Use a spec and do what? Measure the absorption, and then look at your calibration curve that you just created and find the concentration. You need to give me that y equals mx plus b though, because you might need to put that in your calculator. I gave you the ability to do it on the computers, but it might take longer than you need to. You have 5 samples, put it in your calculator, run your LinReg. And then after you get your concentration, you're going to take the concentration you have and find the percent copper and brass. Ready? Okay, let's go. Goggles on, find the same lab group you were with.
So the ones with the colorimeters are from the side. Your cuvettes in the brown little or the white boxes, they're tiny, tiny. Everyone else has little cuvettes next to them. Blank your machine. Somebody needs to start getting some copper sulfate diluted. machine first, guys.
I'm not sure how this thing works.
You know I'm holding it like this.
It's just
So, guys, listen, just to get you started here, you have cuvettes. There are already 3 solutions floating around, 0.4, 0.5, and 1 molar. I have lots of little volumetrics if you wish to prep a different molarity solution, or you can do it in a test tube like we did last time, where you put like 5 and 5, right? And you put 5 of one and 5 of water, and that will really get to half the concentration. You need to get this one right now. Okay? So you have plenty to work with here.
We need the base polarity though. We need like a calibration for people who do anything else.
that's what we do today. We do calculate. Yes.
more songs than
So we need to use.
So she has to serve the table. Which are you?
Alright, 0.5 molar. We got 0.135. 0.135. It's 1.5 from 4
This is not, this is.
So if it's 25 molar and then you put in 25 milliliters and 25 milliliters of water, should that be
Alright guys, so I need one person to be deemed brass person. That brass is in your box already, they need to mass it, and then come to me with the math. I need to know your volume of nitric acid needed. Everybody else can be, you like that later.
We have enough.
We have,
Do you have a slide?
You guys have 5, and I need the only 4.
I need a.
I thought I understood.
What do you have for, what do we have for?
We have 4 this one is 20. We have 30.
When you these track or what do you So this is the active value, or this is like the one that this one is active.
Because right now you have this value. So
Is that 24?
Can you guys go the other way? Thank you. Go the other way. Step I mean, perhaps like now it's taking a while to react.
Five water, five.
Say yeah, you already have a calibration curve. Yeah, all right. Are Darcy, your group's ready? Second group to draw grass, please. Second group for them. Third group to gaining grass. Fifth group.
This one, there, you can go ahead and, did you get any ads on this? No, did you get any on the outside? You gotta implement
Guys, be careful carrying around acid. Like, you'll think you're coming behind them. They don't have acid back there. Alright guys, we leave in 4. Clean up.
There was 18.
Drop your new class, Lucy's right here. I'm gonna get up on the couch before you break the ring. Right here. Over here.
I'll start working on the analysis for the function of peroxide line. I'll try to finish the lab on Friday. I'll try to finish the lab on Saturday.
That's totally fine. When was the CMPS healthy? The sunglasses. Yeah.
Nice, thank you so much. Thank you. I'll see you
Can we come during intervention?
Yes. Does anybody have a molarity of their brass solution? William. Does anybody else have a molarity? I need it.
Point 328784.
Does anybody else have a molarity? All right, guys, listen. Drew, can you cut the fume off for me? Drew, can you cut the fume off? It's one of the switches. All right, so listen as you guys go. You may come back during intervention after school. I'll talk to you guys, but if you don't have a molarity, then use one of these people to do your calculations. Those are going to be the data points that you can use.
Use it for the final calculation. Okay. Bye, guys.
This sounds more like it. It's small, but go with it. If you, what? It just depends on your readings from your calibration. Go with it. Good job today, guys. Good job today. Drew, we come back after school.
Yeah, I was
Thank
gonna do
you. I really scored.
We actually like.
Bye, guys. Let me just text.